In this video, we will present our work on CutS3D, cutting semantics in 3D, for 2D unsupervised instance segmentation. This is work by Leon Sick, Dominik Engel, Sebastian Hartwig, Pedro Hermosilla, and Timo Ropinski. Our contributions are split across 3 steps of our training pipeline. Similar to previous work in unsupervised instance segmentation, we first generate pseudo-masks that, in the second step, are used to train a detection model, and finally, we perform self-training with this detector. We will start with the pseudo-mask generation. The previous state-of-the-art approaches perform multiple graph cuts on a fully connected, undirected graph, made up of cosine similarities between dino features of the image. This cut is followed by a 2D connected components filter. While this approach often works well, there are numerous cases, such as when multiple instances of the same semantic class are grouped together, where this algorithm yields segmentations for semantic groups and not true instance separations. This is because the initial semantic cut cannot be further divided into instances, since the group of objects is not separable in 2D. Instead, our approach leverages 3D information to cut the semantic groups in 3D, yielding true instance segmentation pseudo-masks even when objects of the same class are grouped together. This figure shows an overview of our pseudo-mask extraction pipeline. At the bottom, you can see the previous approach, based only on dino features and normalized cut. We first obtain a depth map from the scene using an off-the-shelf zero-shot monocular depth estimator that is trained without human annotations. From this depth map, we derive a spatial importance map, which we then use to sharpen the semantic graph along the 3D edges, so mainly areas with large changes in depth. Furthermore, we orthographically unproject the depth map into a point cloud representation. Using the semantic cut from normalized cut, we filter the point cloud using these semantics. From ncut, we also obtain the maximum and minimum absolute eigenvalues. These are defined as the semantically most forward and backward points, and we use them as source and sink for our 3D cutting algorithm, effectively connecting the semantic with the 3D space. After performing the local cut, we obtain the final pseudo-instance mask and repeat the process a total of 3 times. The resulting pseudo-annotations on ImageNet now contain better instance separations across a wide range of object categories, such as person and various animal classes. We also reuse the 3D information of the scene for training our instance segmentation and detection model. Since in unsupervised instance segmentation, we cannot assume that all pseudo-annotations are of a high quality, we aim to capture this ambiguity of our pseudo-labels by utilizing the 3D information used for the 3D cut, and call it Spatial Confidence. The local cut algorithm has a central parameter called tau k end n. For objects with partias are very well separated in 3D, varying this threshold always yields the same masks. But where the 3D geometry does not allow for a clear detection of the object boundary, meaning it's not 100% clear where the object border is, varying the tau k n n parameter yields different instance masks. We aggregate these masks across multiple cuts, calculate a pixel-wise average, and use the resulting spatial confidence maps for multiple ways to augment our detector training. First, we use only spatially confident instance for copy-paste augmentation. Standard copy-paste augmentation chooses these objects randomly. Second, we perform alpha blending of the pasted instances and blur the borders. And lastly, we reweight the binary cross-entropy loss of the segmentation model with the per-pixel spatial confidence. Similar to previous work, we perform 3 rounds of self-training with our model. With our final model, we outperform all previous approaches by considerable margins across multiple benchmark datasets for zero-shot unsupervised instance segmentation. The results for zero-shot unsupervised object detection paint a similar picture. The enhanced instance separation is also visible in our model's predictions. For example, our model is able to separate the human and the baby in the first column, as well as the 3 baseball players in the third column. Thank you very much for watching and listening. If you would like read our paper, use our code, or get in touch, feel free to scan this QR code and visit our project page.